Okay, so today we are going to start our notes on section 2.2, there are those notes, dealing with higher degree polynomials. So we'll look at polynomials that are third degree or higher and look at their general aspects. So if I call something continuous, all polynomials are continuous. That is a function that has no gaps, breaks, or holes. When we start talking about rational functions later in the chapter, we'll see functions that are not continuous, as we'll have points where we divide by zero, and dividing by zero is impossible, so it causes these gaps, breaks, or holes inside of our graphs. When I talk about extrema, easiest way to put that, that's just your maxes and your mins, your high points and your low points. When I use the word relative max or relative min, that means right at that point, that's like a little low turning point or high turning point. You know, I might have a max that's bigger than another max, but when I say relative, we're looking, hey, right there's a peak. Almost think of it like mountains. So like if we have like 4 or 5 mountains, each mountain has its own max. One might be taller than the rest and be the overall highest, but each of them has their own peak or max. A repeated zero is a zero that just touches the axis. We will see a power greater than 1. We'll talk about those special repeated zeros towards the end, and they have a multiplicity. The power on your repeated zero is its multiplicity. So something could have a multiplicity of 2 if it was squared. If that factor has to the 4th power on it, then the multiplicity is 4. It has a 3, it's 3, and so forth. So that is our vocab. Let's start looking at this. So 2 basic features of all polynomial graphs. All polynomials are continuous. They always are continuous, and they always have smooth turns. Polynomials will never be jagged in how they move. They'll never make sudden movements. It will always be a smooth movement from turn to turn. So, will the graph, I'll still explain it graphically. I forgot to erase that part. I did want to write that down with you guys. That was my fault. Will this graph of x to the 7th look more like x squared or x cubed? Well, I know already because 7 is an odd power, it's going to look more like x cubed. Let's take a look at that. So even powers will look more familiar to other even powers. Odd powers will look more familiar to odd powers. So if I look at this graphically, one tab too far, there we go. If I look at, so I have x to the 7th. Whoa. And from what I remember from a cubic, yeah, this looks more like a cubic function than a quadratic. But just to reinforce that, if I typed in f of x equals x squared, yeah, the blue graph doesn't look very much like the red. But if I type g of x is equal to x cubed, whoop, I did not put that in another line. That's going to cause issues for Desmos. G of x equals x to the 3rd power. The green and the red look a lot more like each other, right? So we notice that the red kind of drops down faster and goes up faster, It seems to be more leveled out in the middle, but in general, they look really, really similar. Definitely a lot more similar than the quadratic. So most odd powers will generally look like a cubic function. Even powers will generally look like a quadratic. Okay, let's talk about, now this is a lot. If you are writing down notes, please do not worry about this. Worry about the pictures and the descriptions below. This is very formal mathematical ways to state this. And I'm going to use that formal mathematical language, but this is a summary of everything above it. So, the leading coefficient test says, based off of your leading coefficient, the number in front, and the highest power, we're able to determine end behavior. So there are two scenarios. When things are even, that's our green and our blue here. And when things are odd, that's our red and purple. So when things are even, if the leading coefficient is positive, both sides are just going to go up. So what this is saying, as x goes to negative infinity, so negative infinity is the left side. F of x, our function, goes up to positive infinity. So basically it's saying left side goes up, and then this says x approaches infinity, or as x approaches infinity, so that's the right side. F of x also approaches infinity. So what this statement in green is saying here is just both sides go up. If you think about it, our normal quadratics, if it's a positive in front, it's that U shape pointing upwards, right? That's all this is. It can get a little funky in the middle and be like twisty and turny, but the ends I know will go up. Now, if I put a negative in front of it, if we think about quadratic, usually if it's a positive, it goes this way. If it's a negative, it flips down. So as x approaches negative infinity, so the left side, f of x approaches negative infinity, goes down. As f of x approaches positive infinity, the right side, f of x also approaches negative infinity, goes down. So if it's an even power and a negative, both sides go downwards. Okay, now we'll talk about odds. Odds say the leading coefficient is positive as f of x goes to negative infinity, that's the left side, as x goes to negative infinity, that's the left side, f of x also goes to negative infinity. So the left side goes down, but the right side's going to go up because as x approaches infinity, f of x approaches infinity. So if we look just at the cubics we just had, the left side's going down on both the cubic and the x to the 7th, and the right side's going up. They could do some weird squiggly stuff in the middle, but the left side's going to go down, the right side's going to go up. When we put a negative in front, that flips that. So if the leading coefficient is negative, as x approaches negative infinity, that's the left side. F of x approaches positive infinity. That means it goes up. So left side goes up. As x approaches infinity, that's the right side. F of x approaches negative infinity. That means it goes down. So the right side goes down and the left side goes up there. So again, for those of you taking active notes along with me because you find that better for you than just reading the post-it notes. Just worry about the pictures and descriptions here. The formal mathematical language you can find inside the notes. I don't want you to get bogged down on that. I want you to look at the big picture of these. So this is our visual representation. Find a lot more students do better with the visual representation than this. You'll get more used to this formal notation as you move forward with calculus. There's going to be a little more focus on that, but for right now, we're just kind of blending the two. So you're ready for it next year. Okay, I'm not seeing any questions on the chat. Those in front of me look like they're doing pretty good. So describe the left and right behavior of this graph. I'm going to do it both formally, mathematically, and in layman's terms. You know, if it's just making more sense for you to say left side does this, right side does that, I'm fine with that answer. If you're figuring out how to state it mathematically, great, good for you. I'll take that answer as well. So here with this, my highest power is this right here. So what I'm going to do is I'm going to rewrite f of x is equal to negative 4x to the 6th minus 3x squared plus 1. So here with this, when I'm looking here, I have this is even because of the power and negative because of right here. Actually, I don't like underlining a negative. That looks confusing. So I can just refer to the previous table. Got somebody coming in a bit. So if I look back, I'm even negative. Both sides should go down. So that's what I'm going to predict right here based off of that. Both sides go down, or we can state it in more formal terms. As x approaches negative infinity, f of x approaches negative infinity. So that talks about the left side. And now the right side, as x approaches infinity, f of x also approaches negative infinity. So this is saying the left side goes down and then the right side goes down. Well, I did this without even looking at a graph. That's the nice part about this leading coefficient test. I don't need a graphing calculator. I don't need any of that stuff to say any of this. However, let's confirm it with a graphing calculator. And for you guys, look, the point of the leading coefficient test is to be able to do this without a graphing tool. However, I can't tell if you use your graphing tool just to confirm your answer, or if you use the graphing tool to help you get to the answer. So if it makes more sense for you to graph it and then tell me, oh, both sides go down or the left goes up and the right goes down, whatever, I can't tell the difference between what order you're looking at that in because you're telling me the same information. So let's take a look. I'm going to delete out my old graphs and type this in. So this said f of x is equal to 1 minus 3x squared minus 4x to the 4th. Or no, to the 6th. And there we go. Now I do have like a max here. I do have some zeros. I have a y-intercept. All that is somewhat important information we'll get to later. All I did to figure those out was just click on them. That's the beautiful part about Desmos. To find them with TI calculators, it is more complicated. We're focusing on Desmos because it's a free tool that everybody can use. And you don't have to go out and buy anything. I don't have to pass out anything to you. Now, when I look at this left side, this just keeps going down forever. The right side keeps going down. So since both sides are just moving in a downward direction, both sides go down. Make sense? So look, I don't care if you graph it first, then describe it, or you just use the leading coefficient test to do it. Again, the goal is to get to just using the leading coefficient test. This way you don't have to be constantly graphing everything. You can start predicting behavior of graphs without even looking at them. Okay. So let f be a polynomial of n degree. That means it has at most n real zeros. So if I have something to the 5th power, I can have up to 5 zeros where it crosses the x-axis. If it was to the 20th power, I could create a graph that crosses the x-axis up to 20 times. If it's just squared, we already know quadratics only have at most 2 zeros. And then the graph will have at most n minus 1 relative extrema. So if something is squared, it will have 1 term. If something's cubed, it can have up to 2. If it's to the 4th power, it can have up to 3 terms. 5th power could have up to 4 terms, and so forth. Let f be a polynomial function. Let a be a real number. List 4 equivalent statements about the zeros. If I say x equals a is a 0, that's one statement about it being a 0. I can also say x equals a is a solution when f of x equals 0. So essentially, it's where it crosses the x-axis. I could say that x minus a is a factor of it. And I can also say a comma 0 is the x-intercept. All of these are different representations of the same idea of, if I go back to a graph, where does it cross the x-axis? Where does it cross the x-axis? Hey, I know this crosses at -1 comma 0 and 0.63 comma 0. And watch this. Ooh, that's something else. If I did f of -1, that's 0. If I do f of 0.63, well, because it's rounded, it's just slightly off. It only gave me 2 decimal places here, but you see that's incredibly close to 0. Those are the points. And yeah, so that's visually that representation. That's all talking about where it crosses the x-axis. So I'm going to give you a second to get that down if you were writing that. I know I just had two or three students come in during this. While you're taking that in for the moment, excuse me, I am just going to double check attendance. I know I got 1 or 2 people to fix. I'm fixing you right now. Okay. So if you did come in later, please make sure to stay just a moment longer once I'm done sharing the screen, even if the bell rings, just so I can confirm your attendance. Okay, so see people in front of me still writing, so just going to give that moment. Then we'll take a look at the next little bits. Okay. So, a polynomial f of x has a repeated 0 at x equals 3 with a multiplicity of 4. The graph f of x touches the x-axis at 3 and has a repeated 0, and it has, sorry, I forgot, I wanted to talk about this first before that. I forgot, I like how they say this, but I want to put it in simpler terms for you first. If I'm told something has an even multiplicity, that means it's just going to touch the x-axis. If something has an odd multiplicity, it crosses the x-axis. I want to look at that visually first, off of these statements, and then I'm going to explain those statements. Sorry, I forgot that I'd like to switch up that order there from the notes they gave me. So even multiplicity will just come down, touch the x-axis, and pop right back up. In odd multiplicity, you may see it level out at the axis, or you may see it just cut straight through, but it will cut through the x-axis. It will cross it. Okay, so let's look at this visually. So if I had x equals 3 as my 0, that could create a function like so. X minus 3. Because there was a positive 3, I make it a minus 3 as the factor. Now, let's say I have a multiplicity of 4, so I'm going to go caret to get it to the exponent and put 4. Now, we notice this just comes down and like kisses or touches the x-axis at 3, right? Just comes down, whoop, there we go, and leaves. So that's the idea of that even multiplicity. I could change that 4 to any even number. I could change that to an 8. And notice it's still doing the same thing. Now it gets kind of more spread out, kind of coming approaching that minimum there. But if I made it squared, again, we see that parabola come down and just touch at this point. Now, the other one said, what if I said my zero's at 4, so that's x minus 4, and has an odd multiplicity like 3? So when we see this odd multiplicity, I see this leveling out here, right? It kind of looks like it levels out, then changes how it turns. That's where we'll see with an odd multiplicity. I could even change that to the 5th, and we'll see very similar behavior right there at 4. Again, it looks like it's leveling out a little more, but we see it just touches at 4. And actually, I can do this. I can zoom way in on this. And then a little more. So again, it looks like it's really there, but as I drag this point, you notice, look, come on, work with me dragging the point. You'll notice this decimal starts getting really, really small for my y until it finally reaches 0 at 4. So To summarize that in the notes, if this has a repeated 0 at x equals 3 with a multiplicity of 4, the graph touches the x-axis at 3. If f of x has a 0 at x equals 4 with a multiplicity of 3, it crosses the x-axis at 4. And that's just what we saw visually. Any questions about that? So we are going to sketch this graph here. I am going to use Desmos to guide everything. Our homework is listed there. I want my zeros, I want maxes, I want mins. Those are going to be our critical points for graphing. Those need to be graphed as accurately as you can by hand. And then give me your end behavior. So you can use Desmos to actually, you are going to use Desmos to greatly help you with this. I do want hand sketches, so I know you can tell me where my critical points are. So f of x equals 1/4 x to the 4th minus 2x squared plus 3. So let's hit home. I'm going to go projector mode for you guys, make it a little bolder to see. So f of x is equal to 1/4 x to the 4th minus 2x squared. Awesome. This is a really good looking one. Plus 3. So this just becomes super obvious with everything. First thing I need are my zeros. All I'm going to do are click on them. These are going to be a little tough to hyper accurately graph because like negative 2.449. Are you going to get exactly where that dot is on the x-axis? No. But you can get close to it, right? Again, same thing with the other ones. So let's record our zeros. So for a problem like this, I will want you to list out what your zeros are. So those are negative 2.449 comma 0. The next one was negative 1.414, was it? Yep. Comma 0. That looks a little sloppy. 414, comma 0. Then the nice part, this was symmetric. That's how I'm remembering these so well. The next one's going to be 1.414, comma 0, and 2.449, comma 0. Now I also want my maxes and my mins. So let me put those points on first. So that's right about here, right about here, right about here, and right about here. Again, accuracy isn't the very best on a hand sketch, but that's why I'm listing out what the actual zeros are. Now I know I have 2 mins. Let's take a look at those. So my mins happen here and here. So negative 2, negative 1, 2 comma negative 1. So let's record those. Negative 2 comma negative 1 and 2 comma negative 1. So that's going to be right here and here. And then I just need my max. Now, again, we see values that are bigger than our max. That's what we mean by a relative max. It's okay. I just care what this particular high point is. Right here, 0, comma 3. Now up here, the graph goes all the way to 5. So it's not the absolute biggest value it has, but right at this moment, it's a peak. So that's what we mean by a relative max or min, 0, 3. So that was up here. Now my end behavior, this did not ask us to describe it, but both sides go up, right? So that tells me I'm just going to draw a smooth curve through these points where both sides just go up. So I just do my best to draw this smooth W shape, and I have now accurately sketched this graph. If I look at that sketch and then I flip back to Desmos, yeah, they look pretty similar, right? Again, I had the accuracy of all these points I clicked on Desmos. That's a beautiful part about Desmos. TI calculator trying to find these zeros, it's a little bit of a pain. Finding these max and mins, not impossible, actually not too hard, but definitely more of a pain than just physically clicking on them. And that's the lovely part about Desmos, is you can just click on them. So that is all for the notes. For the homework, I want you guys to try on pages 109 through 110, 18 through 22 even, 30 through 34 even, and then 68 through 90 even. Again, if you downloaded the PDF file that I gave you for chapter 1, please remember, we're on chapter 2, you're going to need to download the new file. If you're just clicking on it in Schoology, you don't have to worry about that. Stop recording now, as those are notes. This will be posted